Thank you so much. Let's see. Oh, wow. So that's pretty dark. Is that too dark? We're good? Okay. Seems slow to me. Well, it's really such a delight to be here, and thank you so much for your hospitality. It's been an incredible day talking to the students, the faculty about the research you're doing here, meeting with the team who's also developing a space mission here, T-Rex, and just really having a blast. So thanks for your hospitality. So I'm so excited to be able to share with you about the Black Hole Explorer, or BHEX. This is a mission that's being developed right now. It's intended to extend the current Event Horizon Telescope into space, producing the sharpest images in the history of astronomy and taking us right to the edge of a black hole. So my goal in this talk is to kind of give you a sense of where this mission concept is coming from, how it's related to what we've been able to learn over the past few years by taking the first images of a black hole with the Event Horizon Telescope, and giving you a sense of what we might learn scientifically when this launches. So to set the stage, I just want to show this introductory video. And the thing that I love about this is that it collapses basically a century of observational progress into just 1 minute. So this is zooming in on the M87 galaxy, which is tucked in between the constellations of Virgo and Leo. It's a giant elliptical galaxy, but it's also more than 50 million light years away. So with our best optical telescopes like Hubble, all you really see is this diffuse ball of stars with a little jet extending away from it. You can zoom in deeper in the source using radio interferometry. And as you look at higher and higher frequencies, the jet becomes more and more translucent until you get to 230 gigahertz. And this is the first ever picture of a black hole. We released this picture in 2019. And the scales of this image are sort of staggering. So the light here is being produced by gas that comes close to the black hole, and it's heated to about 100 billion degrees. So it's glowing. It's this hot plasma that's glowing in synchrotron radiation. The synchrotron radiation is then bent by the gravity of the black hole. If it comes too close to the black hole, it's captured forever. If it comes close but not too close, it's bent before it escapes. And so the black hole is what's carving out the center of that image. And what's neat is that you can estimate how big the black hole is just by the diameter of that orange donut. And that tells us that this black hole is about 6.5 billion times the mass of the sun. And there are a lot of ways to think about how large that black hole is. I'll just give you two kind of fun ones. One is that you can make any object you want into a black hole if you compress it down small enough. So a black hole is just some amount of matter compressed within its Schwarzschild radius. So if you wanted to make the Earth into a black hole, you have to compress the entire Earth down to about 1 centimeter across. You could hold it on your finger. This black hole is so large that it would engulf our entire solar system. So it's sort of unimaginably large relative to even astronomical scales that we're used to. The other thing is, has anyone here seen the movie Interstellar? Okay, so in Interstellar, there's a fictional black hole. This fictional black hole, it was so big, it was just called Gargantua. But because this was inspired by Kip Thorne's writings, everything has numbers behind it and calculations. So it turns out the M87 black hole that you're looking at here is 70 times bigger than Gargantua. So pretty fun that it sort of defeats our expectations. But the other kind of incredible scale that you have to grapple with is just how small this is on the sky. So this ring is about 40 micro-arcseconds across. That's 1,000 times smaller than a single pixel on an image from the Hubble Space Telescope or the James Webb Space Telescope. And the only technique that we know in astronomy to be able to access these scales is this technique of very long baseline interferometry. So that's the M87. The other target that we spend a lot of time looking at is right at the center of our own galaxy, which is called Sagittarius A star. Now this is famous because over decades we've watched stars in the infrared orbiting around this unseen mass. They come close to that star there delineated at the center, and then they're whipped around, but there's nothing there. And so you can look at these Keplerian orbits of stars, and you can use those to infer how large the black hole sitting there must be. And this has been used to measure that there must be a black hole with about 4 million times the mass of our sun sitting right at the center of the Milky Way. This is the work that led to the Nobel Prize in Physics for Andrea Ghez and Reinhard Genzel in 2020. Now, something incredible is you're seeing these stars get whipped around. It seems like this is an enormous effect. But actually, at the closest approach of any of those stars, the gravitational acceleration that they experience is less than what we experience here on Earth. So they're only coming within a few thousand gravitational radii of the black hole. But even so, this makes a prediction that if you could zoom in much closer, this black hole too should be casting a shadow. And that the diameter of the shadow, you can compute just from the mass m there and the distance d of the black hole. And Einstein's theory of general relativity tells you that the diameter of the shadow should be about 10 times gm over c squared d. So this blue annulus tells you the range of possible shadow diameters. And you can compare that with what we got when we made the first image of Sagittarius star, and you can see that they're perfectly well aligned. So again, this is an amazing triumph of general relativity to predict that there could be objects like black holes in nature, and then to go out and have two independent methods. First, one looking at the stars on large scales to infer what that mass must be, and then seeing that black holes indeed bend light exactly as we expect from general relativity. So something that I want you to take away from this is that the reason it's very difficult to make images of black holes is not because black holes are black. The centers of galaxies are actually some of the brightest regions in the universe. They can be putting out immense amounts of radiation. The reason it's hard to take images of black holes is because they're incredibly small. So this is about the same angular size as an atom held at arm's length. And again, the only way that we know to make images like this is to use interferometry. Interferometry is something that comes up all across the map in astronomy and physics. It can often seem sort of like black magic. So I just want to walk you through sort of a playful example of how that works. And to explain that, we're going to draw some inspiration from ducks. So here's some ducks. They run, they jump into a pond, and they start kicking their feet furiously. So they're there, they're kicking away, and as they're doing that, they're stirring up the water that's close to the ducks. But as you look at this video, what you see is that while the water near the ducks is stirred up and turbulent and irregular, far from the ducks, it's these nice, coherent, outward propagating wavefronts. So again, close to them, stirred up, turbulent, irregular, and then far from the ducks, nice, coherent wavefronts. So the toy problem that I want you to imagine is that suppose that you're standing on the boundary of the pond, and your job is to tell me where in the pond the ducks are. But the game is that we'll say that you are blindfolded, you can't see anything, and you also can't hear anything. So all you can do is you can wade right into the boundary of the pond, and you can feel the sloshing of the water against your feet. And the question is, can you tell me where the ducks are in the pond just from the pattern of water sloshing against your feet? So we're physicists, we make this into a toy problem. On the left here, we're going to have some ducks that are very close together in a pond, and on the right, we're going to have them spread out. And let's let them start splashing and see what happens. So we're going to start with the guys on the left. They start splashing the water. Near the ducks, it's very irregular. Further away, you see those nice, coherent, outward propagating wavefronts. And again, what I want you to imagine is that you're just sitting right here on the boundary of the pond, and you feel the water sloshing up and down. Okay, now we're going to do the same thing for the ducks on the right. They're spread out a little bit more. Same thing, near the ducks, it's very irregular, and then far away, you can see those nice coherent wavefronts, and you're just going to sit right here on the boundary of the pond and see that water sloshing up and down. So the question is, where are the ducks? Now, in these two different cases, the first thing that you could look at is just the amplitude of that sloshing pattern, and it turns out that that will tell you how many ducks there are in the pond, but it doesn't tell you anything about where they are. It's the same in these two cases. But the thing that's quite different is the coherence length. So if you and your friend are both standing on the boundary of the pond, in the case where the ducks are close together, you and your friend can be very far apart and you'll see equivalent patterns. But in the case where the ducks are spread out, you and your friend have to be pretty close together, otherwise you see different patterns. And so it's the coherence length that's encoding the distribution of ducks on the pond. Now this seems rather whimsical, but it turns out it's mathematically equivalent to radio interferometry. So in our case, we don't have ducks in a pond, but we do have electrons. And these electrons are spiraling around magnetic fields, sending out their electromagnetic radiation, the electromagnetic waves in synchrotron radiation. That then propagates, and we space telescopes as far apart as we can, and we sample that electromagnetic signal. And then in interferometry, what we do is we take every pair of telescopes and we compute the correlation between the signals that they see. And it turns out that that is what encodes the image of the source, the distribution of electrons. And it turns out there's also one additional step, which is how do you actually map that correlation structure into the information about the spatial displacement. And it turns out that that's exactly given by a Fourier transform. This was originally discovered by Michelson, actually, and Martin Ryle won the 1974 Nobel Prize for applying it to radio astronomy. But that's the basics of interferometry. There's a lot of complexity to it, but fundamentally we're just calculating the correlation between the electric field at different pairs of telescopes. So pulling all this together, this is the Event Horizon Telescope. It consists of many telescopes all over the world, none of which was actually designed to do this kind of science. So what we did is we took existing telescopes and we added atomic clocks and very high-speed recorders, and that allows them to work together as an interferometric array. And you can see on the right there, it produces this image of the black hole in M87, and the circle is our resolution element for the Event Horizon Telescope. So each of these baselines is sampling one spatial frequency of the source. When we made our first image of M87, it turns out we only had 5 independent geographic locations. So that's not very many, that's only 10 baselines. How can you make an image from just 10 Fourier components? It turns out we have one more trick to play, and that's that we make the Earth part of our instrument. The way this works is that every baseline between a pair of telescopes samples that spatial frequency, which is going to be shown on the right. But then as the Earth rotates, the projected baseline between the two telescopes changes as a function of time. All that matters is the baselines as seen from the source, so projected orthogonal to the line of sight. And so over the course of the Earth's rotation, we actually sample many different spatial frequencies with the same fixed pair of radio telescopes. So here's an example just showing if we restrict our data from the EHT to just 2 telescopes, they sample just this slight sweep of spatial frequencies and we just see a blob on the sky. We can add a third site down in Chile that adds more spatial resolution along that baseline direction. It breaks apart a bit. We add our sites in Hawaii, and you see a little bit more structure there. And then finally, we add the last site in Spain, and we're able to see that full ring of emission around the black hole. So that's how you can make this whole Earth-sized telescope with a very sparse array. But the real question is, what does this tell us about black holes, and what does it tell us about their astrophysical environments? And to answer that, our gold standard is general relativistic magnetohydrodynamic simulations. So these are full 3-dimensional numerical simulations of plasma flowing onto a black hole. And these let us study not just an image of a source, but its dynamics as well. So to put this in context, 1 second in this movie would correspond to 1 hour observing Sagittarius Star, or 2 months observing M87. So the black holes are so small, which means they evolve quickly on the sky, and we can study their dynamics on time scales that are quite accessible. And so the question is, when we try changing all the different parameters of these simulations, which ones can we constrain using the EHT observations? And it turns out that it's very difficult to constrain any of them at all. So here's just one example. This is a simulated image of a magnetically arrested disk. That just means very strong magnetic fields near the black hole that are dynamically important. A here is the dimensionless spin of the black hole. So this is close to 1, which is a theoretical limit for black holes. So it's spinning almost as fast as it's allowed to by nature. And then R high is just a phenomenological plasma parameter that's related to the electron heating. Here's another example of a simulated image. This is one with weak magnetic fields. It's a non-spinning black hole, and it has that same plasma parameter. So this is almost the opposite as astrophysical black holes go. And then finally, here's another one with weak magnetic fields. It's rotating very, very fast, and the negative sign means it's actually a retrograde system. The accreting material is rotating one direction, and the black hole is rotating the other direction. And the remarkable thing is that when you blur all of these to the resolution of the EHT, they're indistinguishable. And so there's many different types of black hole images that are consistent with what we're seeing. Now that's for M87. For Sagittarius star, we have sort of a different situation. Here, I'm just going to put up a very complicated plot where every cell here represents one simulation that we ran. And we apply a whole bunch of different observing constraints based on the EHT images and other constraints as well. And so we're able to rule out many of these models as being impossible. Now, it turns out we've applied all constraints here except one. The one that we didn't apply was the time variability. We look at the variability in those GRMHD simulations versus the variability that we see on the sky. And when we apply this last constraint, all the models are rejected. So you can see that we're sort of pushing our simulations to a breaking point. In one sense, they're very hard to constrain using the images because it's easy to sort of mimic relativistic effects with astrophysics. But on the other hand, it seems like we need a much larger set of simulations if we were going to make conclusive statements about the black hole. Each of these cells might take a month to run on a supercomputer. So they're very expensive. So what we've been thinking about a lot over the last few years is just how do we come up with new observations that would provide unambiguous probes of a black hole spacetime. And to understand that, we can get some inspiration from Charles Darwin. So this is not Charles Darwin, the naturalist, but this is actually his grandson, who was a physicist, a very well-known one. And he was interested in the problem of what would it look like if you put a star near a black hole. And Darwin realized that the image of the star, you would see something that's been distorted and magnified. This is like gravitational lensing. But he realized that there would be more to it than that. So he said, each star, in addition to its direct image, will show a series of faint ghosts on both sides of the black hole. There will be a ghost on its left, just outside 3√3m. Furthermore, there will be secondary ghosts on both sides, still closer to 3√3m, which come from rays that have gone a complete circle around the black hole before escaping to the telescope. The successive ghosts of the sequence crowd together more and more closely to such an extent as exactly to counterbalance their increasing feebleness. Then he added, this result seems to have no practical importance at all. And what's amazing is that Darwin was right about everything except that last sentence. So let's think about what it means for us. So here's the image of M87 from the Event Horizon Telescope. And we think that if we could see with perfect angular resolution, we'd see an image that looks more like this simulated image. The simulated image has this bright ring of emission called the photon ring. And it turns out that this shows up in every simulated image of a black hole. So it turns out that the photon ring is not a ring at all. It's a stack of increasingly sharp subrings. And these subrings are indexed by the number of times that light went around the black hole before escaping to us. So I'll just show you an animation that kind of illustrates this. So in this animation, the black hole is encircled by that red circle at the event horizon scale. And we have rays of light that are passing near the black hole. And they're bent by the gravity before they escape to the distant observer, and they make a rather diffuse image, similar to what the Event Horizon Telescope has seen. But it turns out that if you aim the light rays just right, they can make a U-turn around the black hole. And those orbiting light rays pile up on a thin ring near the black hole. They're piling up on the photon ring. And you can aim the light rays more and more precisely. So if you make them even exponentially more precise, you can get them to land to make actually 3/4 of a trip around the black hole before escaping. And so we just index these light rays, these photons, by the number of times they went around the black hole before they escaped to reach us. And the full image that we see, the thing that's actually on the sky that we can study, is the sum of all of those different images. So the goal would be to make a very high resolution image of a black hole so you're able to lock on to this photon ring and then identify the light that was very deep in the gravitational well of the black hole because those are the ones that are very sensitive to the space-time properties of the black hole. Yeah?
Why is the image not rotationally
Yeah, so there's a few effects there. One is that the space-time isn't rotationally symmetric because we're looking at a spinning black hole at an angle. But then also the astrophysics will break the symmetry. So for instance, most of these images that you'll see are brighter on the bottom. That's where the material is flowing towards us. It's moving relativistically, and there's a relativistic boost that makes it brighter. So both relativistic effects and just classical astrophysical effects will break this symmetry. Yeah. Okay, so here on the left is just, again, a simulated image of a black hole, and on the right are cross-sections in intensity going horizontally and vertically. And you can see that these have this sort of peculiar structure, that you have sort of a big hump of emission, and then you have a narrower one that lives on top of that, and then a sharper one that lives on top of that. And that is exactly the photon ring. That each time it goes around, it piles up closer to this asymptotic curve on the sky, and it adds more and more flux in a narrow region. But where it gets really fun is when you start thinking about what this means for interferometry. So for interferometry, we're usually spending most of our time trying to forget that we're using an interferometer. Like we want to sample these visibilities, do these correlations, make an image, and then analyze that. But what's so amazing about this is that if you look at the interferometric response to the black hole image, it's very easy to interpret. So here, the x-axis is just the baseline length. That's just how far apart your two telescopes are. And the y-axis is the visibility amplitude, and you can think of that as just the correlation between the signals seen in a pair of telescopes. So the very short baselines see the most correlation. And as you go to longer baselines than what we can see on the Earth, all of the complexity you see on those short baselines fades away, and you just have this damped periodic oscillation. And the reason it's such a simple response is that's where the photon ring is taking over. Long baselines see very sharp features, and the black hole is introducing a very sharp feature through its strong gravitational lensing. The other neat thing about this is that the periodicity here is giving you the diameter of the photon ring along the direction of the baseline. And something that you might notice is that there's red and there's blue curves here. That's for baselines that are horizontal or vertical. And they have slightly different periods. You can see the peak of the red and the blue drifting with respect to each other. And the thing that's driving that effect is actually the spin of the black hole. So it turns out that if a black hole isn't spinning, what we call a Schwarzschild black hole, the asymptotic photon ring is a perfect circle no matter what direction you look. But if you let the black hole start spinning, what happens is that the photon ring becomes displaced, and it also gets compressed in the horizontal direction. So by going to those long baselines and measuring the asymmetry of the photon ring, we can directly see whether or not black holes in nature are spinning. And this is of intense interest because right now we're trying to understand what powers things like that enormous jet in M87 that we saw in that first zoom-in movie. And the preferred theory for these now is that those are actually drawing their energy from the black hole itself by slowing down a spinning black hole. So what we want to do is be able to make images where we trace those all the way to their roots, and we can see whether or not they're being dragged by a spinning black hole. Now, I don't have time to get into all the detailed calculations behind this, but I just want to give you a taste of sort of how rich and interesting this connection with the black hole spacetime is. So we're going to zoom in on the black hole itself. The sphere here represents the event horizon of the black hole. Anything that passes within that sphere is trapped forever. And it turns out that for a non-spinning black hole, if you park a photon at exactly 3 times the gravitational radius of the black hole, which in this case is 3/2 times the radius of that sphere, you can put it on a spherical orbit. So light can go in a prograde direction. The space-time is totally symmetric, so you can also have it go retrograde, and you can rotate the plane of the photon's orbit however you like. Now, what's interesting is what changes when you allow the black hole to spin. For the Schwarzschild case, it's a photon sphere, and when you spin it up, it becomes a photon shell. And this also consists of spherical photon orbits near the black hole. So in the equatorial plane, the orbit that's rotating with the black hole has to come inward. It kisses the event horizon. The orbit that's rotating against the black hole has to be fighting against the effect of frame dragging so it moves out. You can still shoot rays over the top of the black hole, but now their plane of rotation is going to be pulled by the frame dragging, but it still lives on a sphere. And so all of these different orbits live on spheres at a particular radius, and to fire a photon at a particular angle, there's only one radius that you can do it. So it's this family of spherical orbits around a rotating black hole. Now, what I want you to imagine is that you just nudge one of these photons just a little bit. So it turns out these are all unstable orbits. So if you nudge them towards the black hole, they're quickly captured by the black hole forever. But if you nudge them just a little bit away, they'll escape to the distant observer. And that's where things get really strange. Because the question is, where do they land on the image seen by a distant observer? And it's not what you think. So the colors here match on the left and the right. The right is the image seen by a distant observer. The coordinates alpha, beta are set. These were chosen by Jim Bardeen, who initially studied this problem. But you can just think of this as a picture on the sky. And it turns out that everything on the left of your image, that's the photons that were very close to the event horizon. The ones on the right of the image, those are the ones in the retrograde orbit. And as you're going around the boundary of your ring on the image, you're actually probing different depths in the space-time, different radii of the photon orbits. So it's this really beautiful correspondence as a sort of holographic mapping that takes you from radius in the black hole space-time to angle on the observing image. And so if we could make images of a photon ring, we can do this, this kind of tomographic probe in the black hole space-time to understand the emission at different depths. And again, Bardeen is the one who first worked this out, and he wrote, "It's conceptually interesting, if not astrophysically very important, to calculate the precise apparent shape of the black hole. Unfortunately, there seems to be no hope of observing this effect." And here we are, 50 years later, kind of on the doorsteps of being able to do this. So what we need to do is to make much longer baselines in the Event Horizon Telescope. We have to go to space. And there are several technological reasons that that's quite challenging. So I just want to say for a few words kind of what those are. One of them in particular is the data rates that are required. So the Event Horizon Telescope achieves some of its sensitivity just by swallowing incredible amounts of data. So to make those images of a black hole took petabytes of data recorded to disks, literally truckloads of hard drives shipped around the world. We can't ship hard drives back from space. And if we were to operate using standard data rates, like what was used on the most recent space VLBI mission, which was Radioastron, we would need to launch a telescope that's the size of a football field to detect the photon ring. The Event Horizon Telescope operated at much higher data rates. So Radioastron was 128 megabits per second, and the EHT today is about 64 gigabits per second. And that is what we need to do for the Black Hole Explorer. And what's exciting is that this is something that has already been demonstrated. So this is using a technique called laser communications. It was starting to be developed a few decades ago. In 2013, they successfully demonstrated laser communications from the moon at 600 megabits per second. And the mission that we're sort of modeling our results off of is one called T-Bird. This is a mission on a CubeSat that downlinked data at 200 gigabits per second. That's 1,000 times faster than Starlink. It's doing that with a 1-watt laser and an aperture of the transmitter that's an inch or something. I mean, it's just incredible. This is possible today. And so one thing that we'd like to do is be the first mission that uses laser communication for science, because as soon as we demonstrate that this technology is viable, it can be used on lots of science missions and allow us to get much more data back from all the flagship missions that are being developed right now. So pulling all this together, the BHEX mission is going to have a 3.5 meter antenna. That's basically the biggest thing you can park inside of a Falcon 9. It'll have simultaneous observations at 2 different frequencies. The lower band is at about 100 gigahertz, and the upper band is about 300 gigahertz. It'll sample 32 gigahertz of analog bandwidth, producing data at a rate of 64 gigabits per second, and it's going to have an orbit of about 20,000 kilometers. This is an example of some simulated data from the Black Hole Explorer, where it can go out to these very long baselines and clearly resolve the periodic signal that we're expecting for the photon ring. We can then take those data and we can say what sort of image would we be able to produce with these. So this is an example of an image reconstruction using simulated data from just the EHT or the EHT with BHEX. And then also we can try to estimate the parameters of the black hole spacetime. So the no-hair theorem posits that astrophysical black holes are totally described by just two parameters, their mass and their spin. There are many measurements of mass right now, and BHEX would be able to make a much sharper one that would unambiguously resolve any discrepancies between all of the existing measurements. And for the spin, this would be the first ever direct measurement of the spin of a supermassive black hole. And so we think that we'd be able to get a spin measurement to an accuracy of probably about 10%. The other great thing about the Black Hole Explorer is it's leveraging all of the work that we've done to build this ground network. So this is just showing on the left is BHEX, where the existing ground radio telescopes are the red dots there. And the yellow stars are potential downlink locations for the optical signal. And on the right, that's the baseline coverage, where every point here is a measurement, and when it fills in that entire disk, that tells you that you have enough information to make images. So you can see it's extending these baselines that we have on the ground substantially. But the other good thing is that it's able to actually fill in that signal so we can make not just images of the black hole, but movies. So this is one example of what we think we might see. This is what was it?
Yeah, in the previous slide, is that 230 and 320 gigahertz for the disease program?
On this one, I think they're stacked, yeah. But I don't remember the exact frequencies that are simulated here. Yeah. So here's where we then take a simulated movie of a black hole, and we're taking an observing campaign that goes over 2 months, where we observe twice a week. You can see with our current EHT, you just see this kind of blurry donut that has some variation, whereas with BHEX, we're able to lock in on some of the detailed motion of these arms of plasma that are going around the black hole. And then you can take the averaged image over the 2 months, and that's where the relativistic features really pop out, and you're able to lock on to the features like the photon ring around the boundary, but then also this very dark region on the inside is something we call the inner shadow. That's actually your line of sight directly into the black hole that never intersects the accretion disk. So there's all sorts of interesting opportunities here. But one thing I wanted to emphasize is that BHEX is a computational telescope. So I heard that some very fortunate grad students today got a lecture on radio astronomy. Is that right? Who are the radio astronomers, the new radio astronomers in the room? Okay, so radio telescopes are amazing. You're recording the data to disk and then forming correlations after the fact. And when you do that, you can adjust for delays in the signals. And so you're basically adjusting your surface after you've taken the data. You can even point the telescope after you've taken the data. It's kind of amazing. And so all of this is actually just taking digital data and trying to convert it into not just images, but movies. And what's so fun about this is the algorithms haven't been written yet. So this particular movie was made at 2 a.m. by 3 of my current grad students and postdocs at a workshop at Vanderbilt. But this is a major open problem for us, and we're looking at lots of new algorithm development that can ingest this data and tell us what it means for astrophysics. So in the current EHT approach, we take our images and we make lots of measurements of them. We compare those with simulations. We come up with these binary cuts, and then we publish constraints. And this is a really kind of sloppy process, and in many ways is very unsatisfactory. So the question is, how can we produce credible posteriors for the physical parameters that we really care about, things like the black hole mass and spin? And for that, I think we really need a fundamentally different approach to interferometric analysis. So one thing that I've been doing a lot with the students and postdocs at the CFA is developing simple toy models for emission in a curved spacetime near a black hole. And then what we're able to do is we're able to constrain these models directly with the interferometric data, where you're modeling the emission and the black hole parameters all in one go, instead of trying to kind of break this out into the different pieces that we do right now. So here's just one example of this. So this toy model consists of just 2 cones of emission, and they're lit up. They have some magnetic fields threading them, and some emissivity profile. So it might sound kind of complicated, but it's just a 13-parameter spherical cow model for the material near a black hole. So on the left here, or at the top here rather, these are 2 general relativistic magnetohydrodynamic simulations. Again, these take a month to run on a supercomputer, incredibly complex, and these are what they look like after you take a time average. MAD, again, is the magnetically arrested disk, so this guy has really strong fields, this guy has really weak fields. And here's with the toy model, the 13-parameter, spherical cow approximation, and it turns out that it's basically indistinguishable from the fully numerical simulation. So I think there's a lot of hope that we can come up with these very simple models for glowing material near a black hole that get down to the very essence of how a black hole spacetime is shaping what we see and allowing us to really lock in on what we're able to learn from them. So this is an example that's very controlled. We're feeding in simulated data. We know what the answer is. We can also apply it to actual data. So this is the first image from the EHT of M87, and this is what we get when we fit our model image and blur it to the same resolution. So it's producing similar images on the sky, and it's actually giving us posteriors for all of these black hole parameters. This is the angular gravitational scale. This is the spin, which is unconstrained, the viewing inclination, which we think we know. So these are very first steps. I think there are lots of reasons to be skeptical of this, but I think for all of those in the audience who are thinking of what cool projects should I do that bring new computational toolkits to astronomy, this is an example of an area where I think there's just a huge amount of growth potential. The other exciting thing is that as we go to longer baselines, we can see more black holes. It's sort of like LIGO, right? For LIGO, they spent decades and decades and saw nothing at all. Then all of a sudden, there was the first event, and now, only a few years later, they're seeing an event every few weeks. And it's the same for us, where if you increase the resolution of your interferometer by a factor of 10, you increase the number of black holes that you can resolve by a factor of 1,000, at least in the local universe. So BHEX will study many sources across the sky. This is a sample of some of our potential targets. The 2 rock stars are Sagittarius star and M87. They have the largest apparent shadows, as seen from the Earth, of any black holes in the universe. But all the red sources here are additional black holes where we think we'll be able to study them on horizon scales. We'll be able to make images with BHEX that are similar in quality to what we have today using the Event Horizon Telescope for M87 and Sagittarius star. And in addition to that, there's all sorts of other types of objects, bright active galactic nuclei and blazars that we'll be able to study not on scales of the horizon, but on scales of tens or hundreds times larger, that tell us how black holes are actually interacting with their environments and feeding energy back into the universe. And what's really special is that these aren't just oddball targets on the sky. They're some of the most exciting objects in astronomy. So just as a few examples, this guy TXS0506, this is the first non-solar neutrino source ever detected in astronomy. Centaurus A is the closest AGN with a limb-Brighton jet. OJ287 is probably our best candidate as a binary supermassive black hole. And this is just a handful of them, and it turns out that all of these sources are very bright at the sub-millimeter wavelengths where BHEX will observe. And so I think there's lots of really exciting possibilities for new discoveries. So pulling it all together, the Black Hole Explorer is going to create a telescope that has a virtual aperture 3 times the size of our planet. It'll produce the sharpest images in the history of astronomy, and it will detect the photon ring of a black hole for the first time. So to a physicist, a black hole is a puncture in the fabric of space-time. And so we're really trying to capture the photons that danced right around the edge of the universe before they only were just able to escape the gravitational pull. And then when they do, they have the imprint of the black hole on them. So the goal is to be able to study them in detail and to make the first ever direct measurements of whether or not a black hole, these supermassive black holes are spinning. We'll be able to study dozens of additional sources, including both black holes and their relativistic jets. And this is being developed as a NASA Small Explorers class mission. So that's a $170 million cost cap. We're expecting a mission proposal next year, and it would launch in 2032. So to summarize, the EHT has captured the first ever images of a black hole. It's made images of M87 and Sagittarius star, revealing their apparent shadows and giving us estimates of their masses. The EHT prompted a global surge of interest in black hole astrophysics, and I think in astronomy and physics overall, and has just been an incredible journey and incredible success story. But this is really just the first glimpse of our first glimpse at the space-time near a black hole, and there's so much more that can be done. And in particular, things like the photon ring show us that black holes actually create signals that might allow us to study them in ways that we've never been able to study other types of sources. So some examples are the photon ring. It's a universal feature from strong gravitational lensing that we should be able to make very precise measurements of using Earth-space VLBI. And in addition, the fact that the source counts are volumetric means that over the coming decades, we should be able to study not just 1 or 2 sources, but eventually dozens or even hundreds of them. So this is all enabled by explosive growth in digital technologies. I think radio astronomy is entering a golden age, and yeah, happy to answer any questions you have at all. Oh, sure, yeah.
Thanks, very interesting. I have a couple of questions. One, is it possible for you to do some pre-processing on board rather than sending, 170 gigabit per second? Then why can't you do the analysis while it's being spinning?
Yeah, it's a great question. So it turns out that to any individual telescope, the signal that they see looks like Gaussian white noise. And the only way that you extract a signal from it is correlating that Gaussian noise with another telescope.
So you still need the Earth-based.
You still need the Earth-based telescopes. That's right. So you could do the processing in space, but then you need to get all the data from the ground up into space. But there's no way, well, there's only one reduction we can do, which is we quantize the data. So we actually reduce it to just 1 bit. And you don't lose very much signal in that case. But there's no compression that you can do apart from the quantization.
Thanks. And a second question, can you possibly measure polarization of the radio waves? And if you can, would it help?
Yes. So polarization is a very rich source of information. It's been a lot of what we've been doing in the EHT recently. And it turns out it's very easy to measure using interferometry. So typically what we do is that you have 2 receivers and you measure either the left and the right circular polarizations or the 2 orthogonal linear feeds. Then you can form 4 correlation products, say right versus left, right versus right, left versus left, or left versus right, and those correspond to the 4 Stokes parameters. So BHEX will measure full polarization of sources, and just one example of how this is really cool is that the polarization image, the polarized image of a black hole tends to have kind of a swirling polarization pattern with a particular curl to it. The photon ring is kind of like looking at the back of the black hole. And if you flip a spiral galaxy over, it switches handedness. So there's a prediction that the direct emission should have a particular handedness. The photon ring should then reverse it. And that would be kind of a smoking gun signature that you're really seeing the light that orbited the black hole. Yeah. Sure.
same radiation, and but this radiation was predominantly on the higher frequencies, and the lower frequency radiation, which is radio radiation, is kind of less understood. So I'm wondering, like, what's the potential of this black hole explorer in kind of detecting this kind of brightest phenomenon?
Yeah, so this is actually a topic that people have looked at for the EHT images. There's a prediction that it should lead to a very particular polarization signal and a particular type of periodicity in it. So there are some constraints. You could look up some papers led by Yifan Chen, published just a couple of years ago. I'm not sure if the Black Hole Explorer would substantially tighten those constraints. It's a good question, and I would have to think more about that. Yeah. Sure. Here.
Has the BHEX team considered an elliptical orbit as opposed to a circular orbit? And I ask this because at perigee you would have greater temporal resolution, and at apogee you could have greater distance and send data down. So is there any benefit of an elliptical versus circular?
Yeah, so I think the orbit you'd really want is maybe something that's quite elliptical, that's tracing out lots of different angles, because you want to measure not just long baselines, but see them at lots of angles. The problem is at the distances we're at, a few tens of thousands of kilometers, there's nothing to gravitationally perturb the orbit. And so you're kind of stuck in whatever orbit you launch, unless you're going to fly a bunch of propellant. So then to get kind of even sampling at all the position angles and make very precise measurements of the photon ring, what we converged on was a circular orbit that lets you do that for M87, and it's actually elongated in projection for Sagittarius star because of scattering. But it could be that there are other orbits that do give other types of optimizations that are worth considering. Yeah.
I just have a quick question about the polarization. So is that linear polarization or circular polarization or different?
It turns out you can do either. You can measure anytime you have orthogonal feeds. You will have some linear transformation that relates whatever four products you can make to the four Stokes parameters. So radio telescopes on the ground actually commonly use dual circular, but also commonly use dual linear, and it's just some linear algebra to go from one to the other. Yeah. Sure.
Following up on the orbits, how did you land on a neo orbit instead of a LEO orbit or a higher orbit?
Oh yeah, so when you're doing the orbit, first thing is you want to go to the furthest you can, right? You want the best angular resolution. And I remember when I started working on this, I was like, we have to do 10 times the Earth, right? We're never going to get this sold if we can't do that. The problem is when you get along orbits, you take two hits. One is that the signal is falling, and so there's actually less correlated signal to see. So if you want to go to the very long baselines, you need to be more sensitive. And the second is that these laser downlink systems are incredible. They're basically transmitting 1 bit of information per photon. So they're incredibly efficient. But what that means is that if you double your orbit radius, you cut your data transmit rates by a factor of 4. Or another would be to think of it as if you double your orbital radius, you increase the amount of power you need to pump into the laser by a factor of 4. So what we found was the 20,000 kilometers is kind of the sweet spot where you can you have long enough baselines to see the photon ring and to do this new science, but you still are able to get the data down without the power requirements being prohibitive. But I think, in the future, there will be fleets of telescopes going out to much longer radii and doing all sorts of neat stuff. Yeah.
So you mentioned that you can have multiple data points because the Earth spins, essentially.
Yeah.
But there's dynamics on the picture. So how do you, I guess, what's the time scale of the dynamics of, say, the photon ring? And how do you fix that issue? Is it just very slow compared to the, okay.
Yeah, no, I think you're touching on the fact that they're actually similar, and this is what makes the analysis quite complicated in some cases.
You make one picture.
You make one.
But you have to somehow average out or fix the time component.
So for M87, the light crossing timescale of the black hole is about 8 hours. The coherence timescale for features in the accretion flow is a few weeks. The orbital timescale light is maybe 30 days or something. So you can basically do all of this stuff in orbit and let the Earth rotate and assume that the source is effectively static. For Sagittarius star, that is not the case. So a day in the life of M87 is a minute in the life of Sagittarius star. Light crossing time is 20 seconds. And so you have this problem that as you're tracing out a single orbit or the Earth is rotating, the source is doing all sorts of stuff. And so that's part of why we need new algorithms to process that. And it's a source of a lot of ongoing work in the EHT right now is how do we even analyze the data we already have.
Even if you go to like BHEX, that problem will be solved, right? You just have, it's the, I don't know, 3 times the number of, very small number of points.
Yeah. So we're looking for.
So you have to, I guess you have to model it, is that what you're saying? And then somehow back it back out?
So I hesitate to say all you have to do is X. It's basically it's a really hard open problem, and open problem in modeling to adequately account for the variability. Yeah.
Is the imaging timescale also going to change with BHEX compared to the EHT because the satellite, like the baseline is changing faster from the satellite moving than the Earth rotating, right? So does that also change the timescale?
Well, I'd say the imaging timescales that you really care about are set by the black hole system. And so you might chunk up your observations in different pieces and make separate images for different ones, but I don't expect that the time resolution of BHEX is going to be substantially different than the EHT. Yeah. Sure.
So in terms of constraining parameters, can you say that it seems that this kind of method is maybe less efficient than constraining parameters using gravitational wave data, but they can be done on a totally different object. Like because if you want to constrain your parameter inverse using gravitational wave data, you have to first detect merger and then do the inverse. But this one you can do it on a supermassive black hole and don't require it to be a merger.
Well, yeah. Yeah, so I think, LIGO and LISA, they're incredible, right? It's hard to imagine a cleaner problem. You have these 2 point masses inspiraling, colliding, right? It's an incredibly beautiful measurement that they can make. Some limitations, right? They only study stellar mass black holes right now, and we're studying supermassive ones, so they are quite different systems. And then LISA will kind of straddle that gap. And I would say even with LIGO, it's pretty tough to make measurements of spin. And the masses, right, you get the binary mass function and so forth. So breaking them all apart to get at the individual elements is still pretty tough. But
There's some degeneracies when you are using LIGO data.
Yeah.
Constraining parameters. I think it's between spin and mass.
Yeah. So I think the closest analogy between what you can do with the photon ring and LIGO would actually be measurements of the quasi-normal modes in the black hole ring down, which is also a very clean problem. But I think they're fundamentally complementary, and I don't think that LISA is likely to measure black hole spin for, say, any sort of AGN with a prominent jet. So these questions of what's the astrophysical significance of spin is something where I think the black hole imaging probably has a unique role to play. But it's a good point, yeah.
What kind of constraints can you put on deviations from Kerr as opposed to just BHT?
Yeah, so this is a pretty deep question. There are certain black hole mimickers that would produce something wildly different. So one example that's just kind of fun is wormholes. So wormholes actually will produce not just a single photon ring, but multiple photon rings, and they can come from light on both sides of the wormhole. So you might look at the galactic center and see, okay, it's actually not a black hole at all, it's a wormhole. That would be cool. Other types of mimickers don't produce photon rings at all. Those kind of extreme examples, I think we could put tight constraints on. In terms of more nuanced cases, it's not very difficult to come up with alternative metrics that are totally degenerate with Kerr. And so I think will this ever be a really precise test of GR that's going to convince the most, stubborn skeptic? I don't think so. It's not really of that category. But I think the stepping stone is just being able to say we understand the black hole's properties, we know them precisely, and the fact that the EHT, we can't make strong spin measurements with the EHT makes me very wary of statements about constraints on GR from the EHT. So I see this as a stepping stone and part of something that we'll be trying to track down over the next century, not something that is kind of a one and done. But, yeah.
One last question. How does the finickiness and efficiency of immediate data downlink affect observational schedules and operational concerns?
What do you mean the finickiness of downlink?
Like just the fact that you were mentioning it's 1 bit per photon and is susceptible to fall off over distance and atmospheric concerns.
Oh, well, so I think what we would like to do is basically fly no memory buffer at all, where you're just dumping the data as you're taking it, and for that you would need a pretty stable link. If we launch and it's finicky and things are coming and going, I would say that would probably be catastrophic. So the goal here is to launch something that has a very stable, extremely high data rate link that gets cut out from time to time from clouds or something else, but that fundamentally is quite reliable. Yeah. And
Quick one. Okay. So in terms of that data transferring with the laser, would it be the same idea with GPS? Like you have a cone, and then as long as you're within that cone, you sort of get the data, or does it has to be pinpoint accuracy?
yeah, so this is actually pretty fun. The radio downlink has a huge beam size, which is great because you don't have to point very accurately, but the downside is it's easy to snoop on radio downlink. The optical downlink is done at 1.5 microns, tiny little beam, very hard to snoop on, great, defense, government applications, but it does mean you need very precise pointing for it. So we're using a commercial vendor for that, and I'm not trying to build that in a lab or something. It's pretty tough, but it's already been demonstrated. This is something that can be done. But I should also say I'm here for a bit and happy to chat with people if you have questions. And yeah, thanks again for your hospitality. Yeah.